Hi, I'm Mark Barsamian. In this video, I'll continue a discussion of area between curves. The subject will be the connection between area between curves and total change problems.
This material is from section 6.1, more specifically pages 390 to 391. These three examples, 3, 4, and 5, are relevant to this video. The corresponding homework is this short collection of two problems from section 6.1. Recall what I called at the time the most important concept of the second month of the course. It was the idea of these three equal quantities that are related to slope. One is the instantaneous rate of change of a function f at x equals a. Another is the slope of the line tangent to the graph of f at x equals a. And the third is the derivative of f at x equals a, denoted f prime parentheses a. The idea that these three quantities are equal is visualized with this diagram. And we referred to that diagram during the second month of the course. When doing problems, we would point out how the problem could sometimes be thought of as exploring relationships that were shown on this diagram. Relationship between those two things, or maybe these two things, etc. It's useful now to identify three important quantities that are equal, that are related to area. So to start with, recall that the definite integral represents a signed area. So this symbol, the definite integral of f from a to b, represents in terms of the graph the signed area of the region between the graph of f and the x-axis on the interval ab. And then recall the relationship between the definite integral and antiderivatives as articulated in the fundamental theorem of calculus that says that this definite integral is equal to this change in capital F from a to b, where capital F is an antiderivative of little f. And recall that the definite integral can be used to find the total change of a function, capital F, from a to b, if the derivative capital F prime is known. So we have talked about what I refer to as total change problems, where the problem is this. Given the rate of change of some quantity, capital F prime, and given two numbers, a and b, with a less than or equal to b, find the change in the quantity capital F. That is this expression. Well, the solution was to use the fundamental theorem of calculus. This difference, this change in capital F of b minus capital F of a, could be found by integrating capital F prime. And realize that that's simply a repackaging of the fundamental theorem of calculus. So we can identify three equal quantities related to area: the change in capital F from a to b, the signed area between the graph of f prime and the x-axis from x equals a to x equals b, and the definite integral of f prime from a to b, denoted by that symbol. We can visualize these relationships using the same kind of diagram that we used earlier in the semester to visualize three equal quantities related to slopes. So this will be an important concept in the fourth month of the course. It's already been, it's just that I haven't presented this drawing yet. In homework 80, total change problems, you were asked to find the total change in some quantity, capital F of x, from a to b, when the derivative, capital F prime, was given. The point of those exercises was that you had to make the connection that the change in capital F is found by integrating capital F prime. That is, you were asked to find this, and you had to make the connection that you found that change in capital F by integrating capital F prime. In homework 84, which is the subject of this video, you're asked to compute areas between the graphs of capital F prime and the t-axis over a time interval, and then you're asked to interpret the result. The point of these exercises is that you must first make the connection that the area is computed by integrating capital F prime, and then you have to make the connection that what that area represents is the change in capital F from t equals a to t equals b. So you're asked To find this, you have to make the connection that you find that area by doing a definite integral, and then in being asked to interpret the result, you're being asked to make this connection, that signed area is equal to the change in the value of capital F. Example 1, bacteria growth rate and change in weight. A bacteria culture is growing at a rate capital W prime equals 0.6 e to the 0.2 t grams per hour. Question A is, find the area between the graph of W prime and the t-axis over this interval. Give an exact answer and a decimal approximation. Well, now, remember that these words, find the area between curves, refer to unsigned area. So what we're really being asked for, I should have labeled this USA, unsigned area equals what? Now remember that in order to find the unsigned area between curves, we have to make sure that we understand which curve is the top curve and which is the bottom curve. Well, remember that e to any power is always greater than 0. So the y values on the curve W prime equals 0.6 e to the 0.2 t, those y values will always be greater than 0, greater than the y values on this curve. So the top curve will be W prime and the bottom curve will be y equals 0. So when we integrate top minus bottom, we're integrating W prime minus 0. In other words, we're just integrating W prime. Now, we could have gotten there without thinking about top and bottom. We could have just observed that for this graph, since the graph is above the axis, the signed area will be a positive quantity, so the signed area will be the same as the unsigned area. But I just wanted to review a little bit our vocabulary of top and bottom graphs and area between curves. The integral is computed on the next page. There you see the definite integral computation, the usual setup. I use the fundamental theorem of calculus to replace that definite integral with this computation involving an indefinite integral. Then I break off the indefinite integral calculation, do it over to the side, bring the results back in. One of the things used in the computation of the indefinite integral was this important integration step here. Remember that the indefinite integral of e to the kx is e to the kx over k. That's one of our indefinite integral rules. The corresponding derivative rule is that the derivative of e to the kx is k e to the kx. As usual, the indefinite integral results in a function form that has a constant of integration. That constant of integration gets brought back as part of the function form and then gets canceled in the first subtraction step. Other parts of this computation are just careful arithmetic. 0.2 times 15 is 1/5 of 15, so that's the number 3. 0.2 times 5 is 1/5 of 5, so that's the number 1. So the simplified result is 3e cubed minus 3e. That's the exact answer. That's the only way to write that number exactly. Now we can type that into a calculator and get a decimal approximation. Now here I just wrote down one decimal place. I could have written down 20. I could have written down 100 decimal places. It would still be an approximation. The only way to write the answer exactly is to write it in symbols, as I've written it here. 3e cubed minus 3e. Question B. Interpret the results of Part A. Well, remember, the result of Part A is an abstract mathematical result. And to interpret that result means to explain what the result tells us about bacteria culture. Well, in Part A, we found the unsigned area using this definite integral, but we observed that that same definite integral computes signed area. Now, the connection that we need to make is, by the fundamental theorem of calculus, the value of that definite integral equals the change in weight of the culture from 5 to 15 hours. That is, this definite integral, by the fundamental theorem of calculus, equals this change, capital W of 15 minus capital W of 5. So we've made this connection that the definite integral of capital W prime equals the change in value of capital W, which equals that area that we computed. The conclusion is the change in weight of the culture from time t equals 5 hours to t equals 15 hours is roughly 52.1 grams. That's the interpretation. Let's go on. It's worth noting that we've done the same problem before. In the video for homework 80, discussing concepts from section 5.5, the question was posed a little differently. It was an example of a total change problem. The question was posed this way. Bacteria culture is known to be growing with this growth rate. The question was, how much does the weight of the culture change from time 5 hours to time 15 hours? Now, in that example, we were being asked to make a different connection, or the connection in a different order. That is, we were being asked to find this change in weight of the bacteria culture. We had to make the connection that that is computed by integrating the growth rate, capital W prime. Now, in that example, we illustrated this change in weight using a picture of the graph of capital W prime, a picture like this. So that red quantity is that change in weight, roughly 52 grams. But we also illustrated this using this graph of W. This is not W prime. It's an exponential function. It has the same kind of shape as the graph of W prime, but this is the graph of the function form for the weight of the bacteria culture. So in this graph, that quantity, the change in weight, shows up as a change in height on the graph. This distance there, this delta W, is another illustration of that change of weight. That's the end of that example. Let's go on. Example 2. A training course estimates that its students learn skills at this rate. Capital S prime of t equals 10 over t plus 1 for t in the interval from 0 to 8, where t is the time in hours spent in the training course, and capital S prime parentheses t is the rate at which skills are being learned at that time t, in units of skills per hour. Question A is, find the area between the graph of capital S prime of t and the t-axis over this interval. Give an exact answer in symbols and a decimal approximation, rounded to the nearest integer. Well, notice that this question is posed using the language of area between curves. So we have to make sure that we understand which curve is the top curve and which curve is the bottom curve. Well, note that the values of this capital S prime will be positive for time t in that time interval. So that means that this curve capital S prime will be the top curve, and the curve y equals 0 will be the bottom curve. So this picture is a graph of capital S prime of t equals 10 over t plus 1. So since we've identified our top and bottom curves, our unsigned area will be the integral of top minus bottom. So the integral of S prime minus 0. So in other words, just integrate S prime from 1 to 3. The definite integral is computed using the usual format. The first thing is use the fundamental theorem of calculus to replace this definite integral calculation with this calculation involving an indefinite integral. And then the indefinite integral details are on the next page. I break off this indefinite integral, do the results on the next page, and bring it back in. So the indefinite integral is, this should say 10 ln of absolute value of t plus 1 plus c. And then I have to compute the change in that from t equals 1 to t equals 3. So the plus c, the constant of integration, gets canceled in the first subtraction step. And then there's just some careful arithmetic. Absolute value of 3 plus 1 is just the number 4. The absolute value of 1 plus 1 is just the number 2. And then the arithmetic of logarithms, ln of 4 minus ln of 2 is just ln of 4 over 2, which is just ln of 2. So the exact answer is this expression, 10 ln of 2. Rounded to the nearest decimal, that's the number 7. Now let's look at the indefinite integral details on the next page. We're integrating capital S prime, which is this integrand, 10 over t plus 1, so we have to use substitution. We let u be the inner function, which is t plus 1. Circle that in green. Now then, u prime will be the number 1, so that means that dt will equal du. That's the equation dt equals 1 over u prime du. That's done in step 2 of the substitution method. Step 3 is to substitute, cancel, and simplify. So here we substitute. We do the green substitution, replacing t plus 1 with u. We do the red substitution, replacing dt with du. And there is no cancellation to be done, but there is some simplifying. I can bring out that multiplicative constant 10. So we end up with, at the end of step 3, this simplified basic integral involving just u, not x. Step 4, we integrate that to get 10 ln of absolute value of u plus c. That's a function form. Step 5, we substitute back, replacing u with t plus 1. So the result is this function form, capital S of t equals 10 ln of absolute value of the quantity t plus 1 plus c. Let's have one last look at our result of step A. The result of step A was we found that that area shown here has value 10 ln of 2, that's the exact expression, and approximately 7. Question B, interpret the results of part A. All right, well, the result of part A is this abstract mathematical result. It's the value of an area computed by finding a definite integral. Remember that to interpret that result means to explain what that result tells us about learning skills. It's helpful to remember first what the result of the indefinite integral means and to simplify it further. Remember that the indefinite integral result was this following function form. The indefinite integral of 10 over t plus 1 was 10 ln of absolute value of the quantity t plus 1 plus c. Two observations will enable us to simplify this function form and to get an actual function. So first of all, note that during the time interval from 0 to 6, the value of t plus 1 will always be positive. So therefore, this expression, absolute value of t plus 1, can be simplified, and we can just write it as t plus 1. So that means that the expression for the function form, capital S of t, becomes this. Capital S of t is 10 ln of quantity t plus 1 plus c. We don't need to keep those absolute values. The other observation is that since capital S prime is the rate at which a student learns skills at time t hours, it's also the rate of change of the number of skills that the student knows. So that means that the value of the function capital S is the number of skills that the student knows at time t hours. If we assume that the student starts, that is at time t0, with no skills, then that means that capital S parentheses 0 has to equal 0. But if we use this formula and we compute capital S parentheses 0, we get that capital S parentheses 0 is c. So that tells us that c has to be the number 0. So the simplified formula for capital S of t is the following function. It's no longer just a function form. There's no constant of integration left. Capital S parentheses t is this expression, 10 ln of the quantity t plus 1. And what that represents is the number of skills that the student knows at time t hours. With that better understanding of what capital S of t means, we can now interpret the result of part A. In part A, we found this unsigned area using this definite integral. But we realize that that same definite integral computes the signed area because the graph of capital S prime is above the t-axis. So the unsigned area between the graph of capital S prime and the t-axis is the same as the signed area between the graph of capital S prime and the t-axis. But the fundamental theorem of calculus tells us that the value of this definite integral equals the change in the number of skills known from time 1 hour to time 3 hours. That is, this definite integral of capital S prime is equal to capital S of 3 minus capital S of 1. So that means that the number of skills that were learned from time 1 hour to time 3 hours is roughly 7. That sentence is the interpretation of the result of part A. Now that number can be illustrated on the graph of capital S, shown on the next page. Here's the graph of capital S of t equals 10 ln of the quantity t plus 1. And remember, what we just discussed is that this is the number of skills that the student knows at time t. So there's the graph with more things labeled, and we see that the change in the number of skills known is illustrated by this height, this difference in values of capital S from t equals 1 to t equals 3. So let's go back and look one more time at our result of question B. Question B was to interpret the results of part A, and our result was this circled sentence: the number of skills learned from time t equals 1 hour to time t equals 3 hours is roughly 7. That's the interpretation of that abstract result. The abstract result was that the area is roughly 7. The interpretation of that result is that the student learns roughly 7 skills during the time interval from 1 to 3 hours. That's the end of this example, and that's the end of the video. Thank you.